So in the nuclear fission, we will start our journey with reproduction factor. Reproduction factor, it is symbolized by K. It is symbolized by K. So K equivalent to, it is a ratio. So it is the ratio of number of neutrons in present generation. Number of neutrons in present generation to number of neutrons in previous generation. Number of neutrons in present generation to number of neutrons in previous generation. So generally, in the nuclear fission, we have a reaction like this: 92 uranium 235. When it is interacted with 0 and 1 neutron, we get 36 krypton 92 and 56 barium 141. So that is, and we have the 3 neutrons emitted. Of course, in addition to this, we have an energy of 200 MeV. So actually, in that kind of discussion, generally we will take, this is the number of neutrons in the present generation, and this is the number of neutrons in previous generation. So when that number of neutrons in present generation is more than the previous generation, so we are having some circumstances. So we are going to discuss that. So the maximum possible values, the maximum possible value of K is 2.5. So because of course it seems to be 3 by 1 equivalent to 3, but all the atoms which are included in the sample may not go under fission. So that's why we are taking on our average of 2.5. And it is observed that if K equivalent to 1, so if K equivalent to 1, that is called as self-sustained chain reaction. Self-sustained chain reaction. We used to call this as a critical stage. And K is greater than 1. So that means the number of neutrons in the present generation to previous generation is more than 1. So then it is called as supercritical stage. And that is an example for atomic bomb. This is an example for atomic bomb. And if K is less than 1, so then this nuclear reaction, it will die out. Nuclear reaction will die out. So that means when the K is less than 1, the number of neutrons in present generation decreases. So then after a while, there are no free neutrons available for the reaction. So therefore, the reaction going to be die. So this is called as subcritical stage. Actually, we will understand this more by discussing nuclear fission. So we are going to see it right now. So here, for the nuclear fission, we are taking power of a nuclear reactor. So this is very important, power of a nuclear reactor. So we are symbolizing its power as P equivalent to energy by time. So therefore P equivalent to NE by P we are taking. So capital N is nothing but number of fissions. Suppose instead of giving number of active atoms available, that is the number of fissions given. Suppose if a sample mass is given, if a sample of mass small m is given, then we will think that, so when we take Avogadro number, so then the mass number is A, the mass required is A, and in the given sample of mass m, let us say we have n number of nuclei. So then we will say n by na equivalent to small n by a, or p equivalent to, instead of n we will write na into m by a, na into m by a into e by t. So here the most important thing is, so generally the atomic mass number, it is taken in gram weight. Generally this is taken in grams. So while we are taking the mass of the sample, so this m also be taken in grams. So that is the most important condition. The general ga mass number అనేది grams లో ఉంటుంది కాబట్టి, గ్రామ్ మాలిక్యులర్ వెయిట్స్ లో ఉంటుంది, grams లో ఉంటుంది కాబట్టి, సో మాస్ ని కూడా ఖచ్చితంగా మనం grams లోనే తీసుకోవాలి. So that is a very important rule here. So that is so because of that complication, this is very famous. Because of that complication only, this is very famous. So here I am taking Na means Avogadro number. Na means Avogadro number, and small m is mass of given sample, and capital E is the energy released per fission, and T is the observation time. T is the observation time. Suppose if E is the energy released, in each fission reaction, then the total energy released E dash equivalent to Ne, we will take E dash equivalent to Ne. So where N is the number of fissions, Okay, so this is about nuclear fission. So actually in nuclear fission, only 0.1% of mass is converted into energy. .1% of mass is converted into energy. Because in the previous example, we have taken when 92 uranium-235 get interacted with 3 neutron gives rise to, we have taken 36 krypton 92 and 56 barium 141 plus 200 MeV. So 200 MeV. So from this calculation, it was concluded that only 0.1% of mass is converted into energy. So after this, we will think of nuclear fusion. So nuclear fusion means, in nuclear fusion reaction, in nuclear fusion reaction. Two are more light nuclei. Two or more light nuclei come together to form a larger nucleus and energy is released. So lighter nuclei, to get stability, they are combined to form a bigger nuclei. Actually, but the desired condition is to participate in nuclear fusion. To participate in nuclear fusion, the nuclei must come together within the range of nuclear force. Within the range of nuclear force. So within the range of nuclear force means in the order of 1 Fermi, we need to bring the molecules. Actually, for this fusion to occur, the nuclei must have an energy. The nuclei must have high energy. That is 0.6 into 10 power minus 13 joules here. And atoms have this much of energy. Extremely at high temperature. Extremely high temperature. We know that the average translational kinetic energy of the gas molecules 3/2 into kBT. So we are comparing the gas molecules. We are comparing the glass molecules. So with the molecules of the sun. So by taking the temperature of the sun as 3 into 10 power 9 kelvins here, so we will get average translational kinetic energy as 0.6 into 10 power 0.6 into 10 power minus 13 joules. So actually, we need to have this much of energy. We need to have this much of high energy for the nuclear fusion reaction. So this is only possible at higher temperature. So generally, as this temperature is not possible on the Earth, so we don't have such lab conditions to do nuclear fusion reactions. So that's why we will conclude that. So nuclear fusion generally takes place in stars. Okay, and we are taking one example, that is solar energy. So that is our daily sunlight or sun radiation is due to fusion. The interior of the sun, has a temperature of 1.5 into 10 power 7 kelvins. These numerics are important. So final conclusion is nuclear fusion is not possible on the Earth. So it is possible in the atmosphere of the stars. So at high temperature. So diffusion in sun involves protons whose energies whose energies are much above the average energy. So that is 0.6 into 10 power minus 13 joules. We have calculated just now. And generally in the sun, nuclear fusion takes place. Nuclear fusion takes place by proton-proton cycle. By proton-proton by proton-protons. So we are taking the proton-proton cycle. We are taking 1H1 plus 1H2 gives rise to 1H 1H1 plus 1H1 1H1 plus 1H1 gives rise to 1H2 plus 1E0. Already we learned, and positron always associated with neutrino. And when we think of this 1H2, that 1H2 after combining with 1H1, it gives rise to 2 helium-3. So here we can see the charge is conserved and as well as mass number is conserved. So we will write a gamma. So this is neutrino. This is neutrino and this is gamma ray. Actually, we will solve this equation. So we will multiply it with 2, and after that, so we will think of the resultant, that is 2 helium-3. Again, it interacts with 2 helium-3. We will get 2 helium-4 plus 2 1H1 to 1H1. So after balancing this, so that means by multiplying the first 2 steps by 2, so we will get the resultant as 4 1H1 gives rise to 2 helium-4 plus 2 1E0 plus 2 neutrino plus 2 gamma ray plus energy. So that energy is approximately equivalent to 24.6 MeV. So in this way, generally 4 protons are combined to produce a 2 helium-4, and in addition to this, we have 2 positrons. So we know that every positron is always associated with a neutrino. Actually, you need to remember this as neutrino. And we have the energy 24.6. So you need to remember one important point is here 0.7% of mass. 0.7% of mass is converted into energy. 0.7% of mass is converted into energy. So that thing we need to remember. And in hot stars, where the temperature is very high, where the temperature is 10 power 8 kelvins. 10 power 8 kelvins. So at higher temperature, carbon nitrogen will take place. Carbon nitrogen cycle will take place. So that is first we will think of 1H1. So it combined with the 6 carbon 12, we get 7 nitrogen 13 excited state. It is in excited state plus gamma. So we will write the gamma ray when everything is conserved. We can see the charge is conserved and as well as mass is also conserved. And this 7 nitrogen 13, which is in excited state, it decomposed to 6 carbon 13 and we will get 1E0. We know that every positron is associated with neutron. And this 6 carbon 13 again combined with 1H1 gives rise to 7 nitrogen 14 plus everything is conserved. Charge is conserved, we can see, and the mass is also conserved. So therefore we get gamma ray. And the 7 nitrogen 14 again combined with 1H1 gives rise to 8 oxygen 15. 8 oxygen 15. Everything is conserved. We have gamma ray. And this is in excited state, 8 oxygen 15. And this 8 oxygen 15, which is in excited state, so it is decomposes to 7 nitrogen 15 plus 1E0. We know that every positron is associated with neutron. So after this, this 7 nitrogen 15 get interacted with 1H1 gives rise to 6 carbon 12 plus 2 helium 4. 6 carbon 12 plus 2 helium 4. So by combining all these, by solving this, again we will get similar expression as to the previous. 4 1H1 gives rise to 2 helium 4 plus 2 1E0 plus 2 neutrino plus 3 gamma ray plus energy. That energy is in the order of 26.7. So this is neutrino actually. We have 2 neutrino. We have 2 neutrino and as well as 3 gamma particles. Generally we use it. So after this, we used to think of the nature of reaction. That is Q value of a nuclear reaction. Q value of a nuclear reaction. So we will take parent nuclei plus a projectile particle. Let us say this is B is nothing but a projectile particle. So that means by which we start the chemical reaction, and T we are taking this T is the target. We get the residual particle R and outgoing particle. R is nothing but this is the residual particle and O will be outgoing particle, or else we used to call this as radiation. So the Q value can be expressed as Q equivalent to kinetic energy of R plus kinetic energy of O, kinetic energy of residual particle plus kinetic energy of the outgoing particle minus kinetic energy of the projectile particle. So in this way, we will find out the Q value of the nuclear reaction, and we know about exoergic and endoergic reaction. So now we will study in another means exoergic reaction. So when Q Q is positive, Q is positive, the reaction is exergic. So when mass of reactants, so that is input, simply we will say, mass of reactants is more than mass of productants. So mass of the reactants is more than mass of products. So that is in the above reaction, MP plus MT is more than MR plus MO. So actually the productants, the elements which are undergoing chemical reaction having more mass than the products. So the input is having more mass than the output. So that means some part is missing. So the part of mass which disappears, it gets converted into energy in accordance with Einstein mass energy equivalence. So already we discussed this in our previous session. So the mass effect appears in the form of energy. And also we need to remember one thing. Q is positive when binding energy of final is more than binding energy initial. So in that case also we have energy release and we have endoergic reactions. So when a reaction is said to be negative, when Q is said to be negative, so that reaction is known as endoergic reaction. So then here mass of productants is more than mass of reactants. So product mass is high. So that means we need to give some more projectile particles. MR plus MO is greater than MP plus MP. MR plus MO is greater than MP plus MP. And binding energy of final is more than binding energy of is less than binding energy of initial. So that means so whenever we see the productant's mass is more, so that means we need to output mass is more than input. So therefore we need energy. Energy is required to continue this process. So to get energy, kinetic energy, so we get this energy in the form of kinetic energy of initial reactants. So actually we are speaking energy is required. Energy is required means so that appears in the form of kinetic energy of initial reactants. And here we need to learn one thing. The minimum energy energy required by bombarding projectile so that is particle to initiate endoergic reaction is called as threshold energy. So that means to start the chemical reaction, we need a projectile, and that projectile having some energy. So that energy is known as threshold energy. So we will write E threshold equivalent to minus Q energy into mass of productants by mass of target plus. So this is important here. So actually, in the given problem, we are taking 90 thorium 228. So after the emission of alpha and as well as beta minus particles. So we have number of alpha particles are emitted and number of beta minus are emitted. So then finally we get 83 Bi 212. In such kind of problems, first we need to think of only mass number, because by estimating the mass numbers, we will easily estimate the number of alpha particles, because this beta minus is nothing but an electron having zero mass. So therefore, just by understanding the mass number difference, so first we will easily estimate the alpha particles. So let us say the difference in mass number. I'm taking mass number difference. Mass number difference. That is 228 minus 212, that equal to 16. 16 means definitely 4 alpha particles are emitted. So when 4 alpha particles are emitted, so then definitely its atomic number of thorium has to be reduced, atomic number reduced by 8 units. 8 units. So that means we get the atomic number as 90 minus 8. 90 minus 8. So that is 82. Okay, actually, after the emission of 4 alpha particles, so the residual nuclei atomic number should be 82. Okay, 90 atomic number ఉన్న దాని నుంచి 4 alpha particles వస్తే ఫైనల్ ఎంత రావాలి, 82 రావాలి. కానీ ఇక్కడ చూస్తే కన్క్లూజన్ లో మనకు 83 అని ఉంది. 83 అని ఉంది అంటే మనకు తెలుసు, by the emission of every beta minus particle, by the emission of every beta minus particle, Z atomic number increases by 1 unit. 1 unit. So therefore 82 is increased to 83. So therefore our conclusion is 1 beta minus particle is emitted. 1 beta minus particle is emitted. So that means we will conclude the equation. 90 thorium 238 gives rise to some 83 Bi 212 plus 4 alpha particles and plus 1 minus 1 is 0. Or we will take it as beta minus. We will take it as beta minus, or we will call it as minus 1 is 0. No issues. So in this way, we will understand the degree. So here it is given that at a given instant there are 25% undecayed. So that means this is active number of nuclei. So we have active number of nuclei in the sample is 25%. After 10 seconds, the number of undecayed again active. After 10 seconds, it is the active number. It becomes 12.5%. So after 10 seconds, its number becomes 12.5%. So that means if we think this is the n is the number of active number, it becomes half. So 25% becomes 12.5%. So this is the half-life time. So first we are taking mean life. Mean life is equivalent to mean life tau is equivalent to, we have the formula 1.44 into t half. That is 1.44 into 10 seconds. That equivalent to 14.4 seconds. And the next question is, after further what time the active number of nuclei decreases from 12.5 to 6.25. So right now we are speaking, we are here. So the number of nuclei decreases from 12.5% to 6.25%. So this is also half-life time. So therefore again it will take 10 seconds. So for the B, the answer will be 10 seconds. So in this way, we will understand the situation. So first activity means A means lambda into n. But the number of active nuclei is not given. So first we need to find the number of active nuclei. N equivalent to, when the mass is given, we have a shortcut m by a into Na. So after taking this, we will get m into Na by a. So this is instead of n we are writing, and lambda means this is 0.693 by t half. 0.693 by t half. So we are taking. So the important thing is, so as the mass number is expressed in grams, so the given weight also should be taken in grams. So that is the important thing. Small m is nothing but 1 milligram. Milligrams we are taking. Avogadro number is 6.023 into 10 power 23 into 0.693 by mass number is 90 grams into 28 years. 28 into, for every year we have 365 days, and for every day we have 86,400 seconds. By doing this, we will get 5 into 10 power 9 disintegrations first. So this is the question. A radioactive sample has 6 into 10 power 18 active nuclei. So this is the n naught, let us say, the original number of active nuclei. How many of these nuclei will still active? So that means n we need to find out after 2 half-lives. So that is n equivalent to 2. n equivalent to n naught by 2 power n, we have the formula 6 into 10 power 18 by 2 square. So that equivalent to 1.5 into 10 power 18. So it is given that a sample having a half-life of 14 days. So therefore I am taking t half equal to 14 days, which contains phosphorus, have initial activity 10 microcurie. So that is A naught equivalent to 10 microcurie. First we are focusing on A. Find the activity after 42 days. So that means A we need to find out, and the time is given as 42. So we know the time equivalent to n into t half. This is a formula that equal to 42. Already half-life is given as 14 days. N into 14 equal to 42. So that means 3 half-lives are completed. We have the formula for activity A equal to A naught by 2 power n. A naught is nothing but 10 by 8, that equivalent to 1.25 microcurie. And one more discussion is, so initially it have an activity of 10 microcurie. After what time the activity reduces to 2.5 microcurie. For this is taken as A naught, and this will be A. So we will write A by A naught equal to 1 by 2 power n. 2.5 by 10 equivalent to 1 by 2 power 4. So 1 by 4 equal to 2 power n. Therefore n equivalent to 2. The time required is t equivalent to n into t half. N is 2 and half-life is 14 days. So therefore we are taking it as 28 days. So here we have a problem. A sample contains 2 radioactive nuclei. So one we will call it as A and the other is B. The number of atoms, the initial number of atoms of A to the B is taken as 3. The rapidly decaying isotope has larger mass. So that means we are having larger mass is A, we are taking. Its activity, original activity of A, we are taking it as 1 microcurie. And the half-lives of 2 isotopes is 12 hours and 16 hours. So 12 hours and 16 hours. We are taking half-life of A as 12 hours and half-life of B as 16 hours. So this is a given data actually. After 2 days, we need to find out. So T is equivalent to, we are writing N into T halves. So let us see how many half-lives are going to be completed for A. So the time is 48 equal to Na into half-life of A is 12. So Na equivalent to 4. Similarly, the time equivalent to Nb into half-life of B. So that is 48 equal to Nb into, that is 16 hours. So therefore Nb equivalent to 3. So the first question is what is the activity ratio? Activity of A by activity of B. So activity ratio means A equivalent to lambda into N. Generally we used to think. So lambda into N means actually lambda means 0.693 by T half, and N means N naught by n naught by 2 power n, n naught by 2 power n. So this 0.693 is a constant, and all these are variables. N naught by t half into 2 power n. So all these are variables. So we will write n naught of a by n naught of b into 2 power n of b by 2 power n of a, and t half of b by t half of a. That equal to n naught of a by n naught of b. So that equivalent to 3 into 2 power n, that is 2 power n of b is 2 cube, and 2 power n of a is 2 power 4, and t half of b is 16, and t half of a is 12. So by doing all these things, we are going to get 2 each one. So this is about activity. Suppose active number means n equivalent to n naught by 2 power n, we are going to see. So that is Na by Nb equivalent to n naught of a by n naught of b into 2 power nb by 2 power na. So same story, 3 into 2 cube by 2 power 4 we are taking. So therefore we will get 3 by 3. So in this way we will discuss key models.